So now we get to a different type of problem. They look sort of similar, but one difference that we might see are things like cos squared x in them. Whenever we see things like this or terms like this with like terms, we can always think about factoring. Factoring is our friend, right? And it can really help us solve trig equations sometimes. So starting off with the first question, A, how do we solve this? This looks like a mess, right? We got secants, we got cosecants, but you'll notice both terms there have a cosecant x, right? So the first thing we should think of is factoring out that cosecant x. Let's see what happens when we do that. Cosecant x, and then what's left of the first term is going to be secant x. And then the second term, once we take out that cosecant x, is just going to be 2. And that whole thing equals 0. Okay, now what do? We've simplified it a lot, actually, but now what do we do? Well, remember what this is. When we're dealing with regular variables and we factored it, in order to find a solution, we need to find what makes this equal to 0, and we need to find what makes this equal to 0. So that's essentially what we're going to do now. We're going to break this up into two separate problems. Where does cosecant x equal 0? And that's what that means. Where does cosecant x equal 0? And where does secant x minus 2 equal 0? Okay, so we can do this. The first one, where does cosecant x equal 0? Let's think about that. First of all, cosecant is ugly, right? So let's change that into 1 over sine x equals 0. Where does 1 over sine x equal 0? I'd like to flip both sides here, right? Do like 1 over both sides to get the sign in the top, but can we do that? The answer is no, right? Because then we'd be dividing by 0. So we can't actually flip that. But another way to think about it is there any value on the bottom that's going to make this equation true? That's going to make this equal to 0. And the answer is no, because if we find something that makes sine x equal to 0, we're going to be dividing by 0. So there's actually no solution to this, right? There's nothing here that we can put down here that's going to make this equation true. So there's actually no solution from this side of the equation, from this root to the equation. So let's look at the other root of the equation. Let's try to solve for x here. Well, we can just move the 2 to the other side to get secant x equals 2. Now let's flip both sides of the equation. Secant is equal to 1 over cosine, right? So 1 over cosine x equals 2. And then let's flip both sides to make that cosine on top. So cosine x is just going to equal 1/2. Well, where does cosine x equal 1/2? This is where you can use your magical unit circle or whatever method you like to do to figure this out. Where is cosine positive? First of all, it's going to be positive here and here, right? And where is that cosine value going to be equal to 1/2? You can do inverse cosine if you're not comfortable with your unit circle, but if you are, you know that that's going to happen. Cosine x is going to happen when this beta angle, this angle in here, is equal to pi by 3. I didn't really draw it to scale. That angle should be a little bit more steep. But the answer here for beta is it's pi by 3. Right? So our beta would be pi by 3. So in order to solve for x, because again here we're asked to find between 0 and 2 pi, right? So our x1 is going to be that angle in there, which is just going to be pi by 3. And our x2 is this angle all the way around here, right? So x1 we can find is just going to be beta, so it's going to just be pi by 3. And our x2, it's like we're going all the way around the circle minusing pi by 3. So it's like saying pi minus pi by 3, which gives us 5 pi by 3. Oh, that should be 2 pi, sorry, 2 pi, right? A full circle minus pi by 3 gives us 5 pi by 3. Are these the only two solutions between 0 and 2 pi? And the answer is yes. We didn't have any horizontal compressions or anything, nothing in here 2 or 3 or any other value to make that not true. So essentially we have two solutions, and these are our two solutions. And notice again how there was another root that we took into account, but this root actually had no solution. So nothing here could make this equal to 0. So our only two solutions were pi by 3 and 5 pi by 3. And what's actually nice to do, I really should have done this in previous questions as well, but we should list our answers at the end. And it's good to list them in ascending order. So pi by 3 is our first answer, and 5 pi by 3 is our second answer. So there we go. That is our final solution to this problem. Okay, this one looks a little bit different. We got a cos squared x in there, and then a cos x. So this is complicated because we have like a squared and then a non-squared one. So one thing we can do is first of all realize what cos squared x actually means. Cos squared actually means cos x squared, right? If we get rid of that 2 there. It's like saying 2 times cos x squared plus cos x minus 1. So one thing that I like to do to make this simpler is to make a substitution. So instead of writing cos x over and over again and trying to factor that, why don't we just let cos x equal u, right? So if I was to do that, if I was to make that substitution, we'd end up with 2u squared plus u minus 1 equals 0. Can we factor this thing? That is the question. Because if we can factor it, we can find solutions. We can plug cos x back in and try to solve, right? So the question is, can we solve this? Can we factor this? And using a little bit of decomposition, you should realize our solutions, our product and sum are going to be negative 2u plus u minus 1 equals 0. And then we factor by grouping 2u, u minus 1 plus u minus 1 equals 0. So our final factored form would be 2u plus 1, u minus 1 equals 0. Okay, so we have that in factored form now, right? It's fully factored. So now what we can do is plug that cos x back in, now that we have it factored, right? So we can rewrite this as, instead of 2u, it's 2 cos x plus 1, and then cos x minus 1 equals 0. So what's going to make this equation equal to 0? And the answer is whenever this equals to 0 or whenever this equals to 0, right? Same thing with solving a regular quadratic. Now we're just got a quadratic with cosines in it, right? So what makes this equal to 0 and what makes this equal to 0? So the equation here is going to be 2 cos x plus 1 equals 0, and here it's going to be cos x minus 1 equals 0. So I urge you, try this yourself. Try to solve for these x's and see what you get as your solution. Pause the video here and try it yourself. Unpause and I will reveal the answer to you. So here we go. On the left side, that 2 cos x plus 1, what we do is we solve that for cos x equals negative 1/2. And using your unit circle, you should be able to come out with the 2 answers. But if you prefer to find your related acute angle, it ends up being pi by 3. So we have our 2 answers. This one here is going to be pi minus pi by 3. And this one here, our x1, actually switch the numbers. But this answer here is going to be pi plus pi by 3. So that gives us our 2 answers of 2 pi by 3 and 4 pi by 3. The second question is, or the second part of it is, where does cos x equal 1? And if you think about it, that only happens when we're at 0 degrees. Or if we go all the way around at 2 pi radians, right? So let's look at the question again. Zoom back out. Where the solution, we're looking for the solution where x is between 0 and 2 pi inclusive, right? So if 0 is a solution, it counts. And if 2 pi is a solution, it counts. So we actually have 4 whole solutions to this problem. So listing them out, x has got to equal, in order, 0. The next one will be 2 pi by 3. Then we got 4 pi by 3. And then 2 pi. Those are our 4 solutions to this problem. Okay, let's try C. So the first thing to do is try to isolate that cos x, right? There's actually a few ways to go about doing this one. But we'll stick with the obvious one first, what I think is the obvious one at least. Let's move that quarter to the other side, and we get cos squared x equals a quarter, right? Now remember, cos squared x just means the entire cos x thing is squared, right? So can't we just take the square root of both sides? If we do that, what are we going to get? Well, this side is just going to end up being cos x, and this side, we just take the square root of what's on the top and the bottom, is just going to be 1 over 2. Is that it? Well, remember, when we take the square root of both sides, we have to be careful. We don't want to lose a solution. There's actually two possible solutions to this, and that's plus minus 1/2, right? Because negative 1/2 also, when we square it, gives us a quarter. So there's actually two solutions here, 1/2 and negative 1/2. So the question is, where does cos x equal 1/2, and where does it equal negative 1/2? So just drawing out a sketch, cos x is positive up here and down here. Cos x is negative over here and over here. So that tells us, just by our quick sketch, right, that we're going to have 4 solutions to this, right? And we can easily find our beta. Again, this is one of our values on our unit circle, so you should be able to find beta, the exact answer for it, and beta is just going to equal, where does cos equal 1/2? That's going to be at pi by 3 again, right? So our beta angle here is just going to be pi by 3 and pi by 3. And then on the other side, when cos is negative 1/2, it's going to be the same thing, right? It's still going to be pi by 3. Pi by 3 and pi by 3. So we basically just need to find those 4 angles, right? So I'm going to actually call those angles. I'm just going to label it here, actually, x1, x2, x3, and x4. So x1, just by looking at it, is just going to be pi by 3, right? x2, it's like you've gone around half of the circle, so pi, minus pi by 3. Which brings us to 2 pi by 3. x3 is like you went around pi plus pi by 3, which gives us 4 pi by 3. And then our x4, our last answer, it's like we went around 360, we went around 2 pi, and we subtracted pi by 3. So that's going to be 5 pi by 3. There we go. We have our 4 solutions to this problem. 1, 2, 3, 4. All those solutions fall between 0 and 2 pi. This last question, D, looks a little bit messy because we have 2 different trig ratios in there. We have cotangent and we have secant squared x. So whenever you have this, we might need to use some identities, right? So the first thing you think of, cotangent, we know that's obviously 1 over tangent, right? So is there a way we can make secant look like a tangent? And if you remember, or maybe just look back at your formula sheet for your identities, you can maybe remember that one of our identities is that secant squared x, it's one of our Pythagorean identities, is just equal to 1 plus tan squared x, right? So if we replace that secant squared x with a tan, right, and that cotangent with a tan, maybe we can do something with both those tans. I'm just going to write it down here to make a little bit more space. So 2 cotangent x is the same thing as saying 2 over tan x, right, plus 1 plus tan squared x equals 0. Right, so that's what our equation becomes because we used this identity, right? So now what I'm going to do is I'm going to get rid of that ugly fraction. See, there's a fraction, that 1 over 10x, or that 2 over 10x. So what I'm going to do is I'm essentially going to multiply everything by the denominator, 10x, right? And I can do that to both sides. 0 times 10x is just going to be 0, though. It doesn't matter. But what I'm going to end up with is 2 plus 1 times 10x is just 10x, plus tan squared x times 10x is going to be tan cubed x equals 0. So I have a relation here, or an equation here. I'm going to rearrange it again so that it's in descending order, like we're used to saying. Tan cubed x plus tan x plus 2 equals 0. And how do we go about solving this equation? Well, again, that's sort of ugly. So I'm going to make a substitution. Let u equals tan x. So then my equation becomes u cubed plus u plus 2 equals 0. Okay, this maybe is bringing back nightmares from an earlier unit in the course, but we do have to factor this thing, and it is a cubic function. Luckily, it's not that difficult to factor. We are going to have to use factor theorem, but it's not that bad. So we can think about it. Remember, factor theorem, we have to try to find a number that goes into that equation to make it equal 0, right? So the factors that were going to be possible are 1 and 2, multiples of 1 and 2. So if I just go through a few things, I can just by inspection sort of see that if I plug in f at -1, -1 cubed is just -1, plus -1 plus 2 is going to give me 0. So -1 works nicely for that, right? Not too much thought required to find that. Once we have that, we can do our division, right? I'm just going to do synthetic division. So again, our equation, I'm just going to rewrite it here. U cubed plus 0u squared, right? Plus u plus 2. I'm just going to write that 0 so that we remember to put that value in there. What goes here for our synthetic is -1, which is the number that plugs into our equation to make it true. And then here, just go the coefficients, 1, 0, 1, 2. Drop that 1 down, multiply by -1, so 1 times -1 is -1. This becomes -1. -1 times 1 is, sorry, -1 times -1 is 1. That becomes a 2. We add, -1 times 2 is -2, 0. 0 remainder, which is what we want to see. So remember, what this tells us is that, well, this part, f at -1 equals 0, that tells us, therefore, x plus 1 is a factor, right? Is a factor. And then dividing, this tells us that x squared minus x plus 2 is a factor, right? So our final factored form is going to be x plus 1, x squared minus x plus 2. And that we know equals 0, right? Oh, I used x's here. These should definitely be u's, right? U is the variable that we're using. Because remember, those are still 10 x's, right? Now, something to look at. We now have two things that we need to basically solve for, right? We need to solve for when this equals 0, so u plus 1 equals 0, and when u squared minus u plus 2 equals 0. Looking very quickly, we see this one's easy. It's where u equals -1, which we're going to plug tan back in a second. But for this one here, if we just take a very look at the discriminant, b squared, which is -1 squared, minus 4ac, this is actually going to, the discriminant's going to be negative. So that tells us right away that this is going to have no solution. So it doesn't matter, we don't even need to plug in the tan there because there's no value of u here that's going to make this true. So no solution. But over here, we can find a solution, and it's going to be where u equals -1. That's going to be when we plug in our tan. Remember, u just equals tan x. Where does tan x equal -1? So this is where we can use any method we want. You can draw out your sketch. Where is tan going to be negative? Well, it's going to be here and here. We can find our beta either by just using our calculator, right? Or by thinking about it. Tan of -1 is like saying where is the slope equal to -1? And that's going to happen at 45 degrees. So basically where beta is pi by 4. Okay? But you can use whatever method you want for that. I'm just going to put beta equals pi by 4. Yeah, you can just use inverse tan to find that as well. So beta equals pi by 4. So that means our x values, our x1 is going to look like this, and our x2 goes all the way around like that. So that tells us our x1 is just going to equal pi minus beta, pi minus pi by 4, which is going to give us 3/4 of pi, right? And x2, it's 2 pi minus beta, which is like 7/4 of pi, right? And those are our solutions, right? Those are the two things that make this equation true. Remember, we did factor it, but we found that the second factor is not going to have any solutions. So these are the only two possible solutions for this equation. Again, a nice way to check your work if you want is to throw this equation into Desmos. This one actually looks sort of cool. This function looks sort of cool when you throw it into Desmos, so give it a shot, and you'll see that these are the only two solutions. So we should write that out nicely at the end. X is equal to 3 pi by 4 and 7 pi by 4. There we go. There's our final answer.